So we're switching gears. So we've gone, for the last couple of weeks, we've talked about systems of differential equations, eigenvalues, eigenvectors. We've almost gone to the point where we're kind of comfortable with those ideas. And now we're going to go and do something completely different. So yay! What's our completely different thing? Well, we're going to think about a different way of solving our problems. So in our class, we're like, well, we have a differential equation problem. We abbreviate ODE, ordinary differential equation. And we said, okay, we've been learning how to solve it. Great. But we've solved lots of problems before. And we've gained skills and abilities. And wouldn't it be nice if we could use those skills and abilities to help us solve our problems? And so one of the things that often happens, and this is a common idea in mathematics, is, can I transform my problem into something that I've done before? Or can I transform my problem of one type into a problem of a different type? And so the idea for the next couple weeks is we're going to talk about a tool that allows us to do just that. And in particular, a type of thing that we've gotten really good at over the years is algebra. And when I'm talking algebra, I'm not talking about very sophisticated algebra. I'm talking about algebra we learned in high school, maybe even junior high school. And so we know how to work with algebra. And oftentimes, there's this idea of like, well, I have an algebra problem. I know how to find an algebra solution. And in particular, what I'm talking about when I talk about algebra, the main tool here is simplifying. So we've learned all these tools from algebra on how to simplify. And so what we can do is we can transform our problem. And in particular, we can say, all right, instead of thinking of our problem in terms of a differential equation problem, I'm going to transform it into an algebra problem, use the algebra tools to solve that algebra problem, and then we're going to transform it back, and we'll have the solution to our original problem. So the moral is, instead of doing the direct solution, we're going to go sort of around this way. Now, it's not necessarily the case that the problems that we're going to see are impossible problems that we couldn't do before. Many of the problems that we're going to see are like, oh, we could do this before. But this just goes to show you the power of the method, because eventually, the farther you go, you run into things that you can't do. And that's what we want to get to. So our focus is going to be mostly on how do we get back and forth. And this is where the idea of what's called the Laplace transform comes in. All right, so what is this? Well, so the Laplace transform, and then there's this key word here, operator, is going to take a function and it's going to produce a new function. Now, when you hear the word operator, that has a particular meaning. And I like to think of the picture that looks like this, where an operator says, take a function, do something to it, and produce a new function. Now, we've seen operators before. Can you give me an example of an operator that we've seen before? Something that takes a function, does something to it, and makes a new function.
d over dx.
Like d over dx. The derivative. Great example of an operator. There's another operator related to it. The integral. Antiderivatives. So these are examples of operators where we take a function and make a new function. And that's what this is doing. So our operator, the Laplace operator, which we can nickname the Laplace transform, we feed it a function. We'll call f as a function of t. And it goes through, and here's the rule. So for every value of s, it produces a number. Now you can let s vary, and therefore you get a function of s out. So we have this function of s coming out. Now, from our perspective, there's a couple of nice things happening here. Now, really, there's many nice things happening here. The nicest thing that we won't see today, but we'll see in the very near future, says, hey, this is useful. But the nice thing for us that we see, we like exponential functions. One of the things that we've seen over and over again is exponential functions are our favorite functions when it comes to differential equations. So that's pretty cool. And the other thing is, we like integrating stuff. Because if you think about differential equations, really our goal is to find somehow the antiderivative of certain functions. So the fact that it has exponentials and there's integration involved, that's a pretty good sign for us. All right. Well, we should talk about some basic properties and facts. So the Laplace transform, and I'm going to probably flip back and forth during class. Sometimes I'll call it Laplace transform, sometimes I'll call it Laplace operator. But the Laplace transform, it works for functions which don't get too big. Now, there's some technicalities. There are functions which grow really, really fast. And the problem is if you grow too fast, the e to the minus st can't slow you down enough. But for all the functions that we care about are usual suspects, if you will. Things like the exponential function, sine, cosine, or t to a power, those are perfectly fine. And we can do the Laplace transform on those functions. And one of the goals for today is to actually do the Laplace transform on all these functions here. Now, we're basing it off of integration. Integration is nice. Has wonderful properties. So one property of integration is that it's linear. That means if I want to integrate the sum of two things, I can integrate each one individually. If I have a constant on the inside, I can pull a constant out. And so I can say that the Laplace transform applied to some constant f of t plus some other constant g of t, well, I can separate, that's the plus, separate it, and I can pull out the constants. So that says really I can do the transform on the individual pieces. This will come up later on, not so much today, but again, if you think about integration, you might have a piecewise continuous function. So that's a function which you say, well, between 0 and 1 it has this type of behavior. Maybe it behaves like sine. Between 1 and 10 it behaves like t squared. Between 10 and a million it behaves like something else. We can take the Laplace transform of such functions because we can integrate such functions. So if you have piecewise functions, you just look at each individual piece. And we'll see how to do that actually very efficiently. Now the next bullet point, this gets into something which is not that exciting to say, but it's kind of useful in the background. It says, hey, if two functions are the same under the Laplace transform, and they're both continuous functions, it had to be the case that the original functions agreed. So in essence, it says the output should be unique. If I have two different functions, I should get two different answers. That's what this is saying. And what's the nice thing about that? Well, the nice thing is that says we should be able to go back. So we have a notion of the inverse Laplace transform, which says, oh, I have this f of s, I should find the f of t which it corresponded to. In terms of the picture, the inverse Laplace transform says run the machine backwards, feed the output in what was the input. Now, is there a formula? Not a simple one, not one that we're going to write down. So how are we going to do it? Well, what we're going to do is build up a collection, a large collection of formulas. And that's going to be today. It's just formula after formula after formula. And you're going to start getting nervous and saying, Steve, do I have to memorize all the formulas here? And the answer is no, you don't. We'll give them to you. You don't have to memorize the formulas, but you have to understand the ideas. So that's what you should be focusing on, understanding the ideas. The last thing I just want to point out is where does the Laplace transform live in this picture? The Laplace transform is what we're going to use to transform our differential equation problem into an algebra problem. The inverse Laplace transform is where we're going to take our solution and figure out what was the answer. So there we go. All right, so that's where our pieces are. The rest of today, it's going to be fun. Let's just try to find as many formulas as we can for the Laplace transform. Any questions before we get going? All right, good. Then let's begin. So we'll start with some very general results here. So not worrying about specific functions, but these are rules. So the first one says, okay, suppose I have the Laplace transform of f of t is f of s. What happens if I scale the inside? So I multiply c times t. All right, well, what's true? We have that the Laplace transform of f of t, we'll just write that down for reference, 0 to infinity, we have e to the minus st f of t dt. So that's the definition of the Laplace transform. Okay. Now we'll take a look at the Laplace transform of f of c times t. Okay, so, well, what should we do is we should plug in the definition. So here, this f of t says that's what we're plugging into the transform. And so we see that whatever we plug in, that's what goes into that slot. So in our case, we see that when we put it in f of c times t, we'll get e to the minus s times t, f of c times t dt. So I'm putting f of ct into my slot. All right. Well, what can we do to make this look more like that? What are some, I think, integral tools? What are some integral tools we can do?
Take the constant out of the integral.
How do we take the constant out of the integral? Because this constant is right now inside a function. How do we take that constant and pull it out?
Use substitution.
Okay, we can use substitution. Now, do you want to use the symbol u? Should we use a different symbol? It doesn't really matter. All right, we'll go with u for right now. So if I use u, I'll do the inside piece. That's c times t. So c t. Or we could say 1 over c times u is t. That's another way to write that expression. So, taking the derivatives, 1 over c du is dt. So, now we go forward. Equals, okay, integral, e to the minus s times t. What will that become? Yeah, well, wherever I see a t, I can replace it by 1 over cu. So that's e to the minus s 1 over cu. F of c times t. F of u dt. 1 over c du. All right. So far, so good. Now, one other thing we have to do. What do we need to worry about? The bounds. Yeah, this is a definite integral. We've got to update the bounds. Now here, I'll put a little caveat. Let's assume c is positive. Just because that will affect our bounds. But all right, assuming c is positive, what do we see? Now these bounds here, these are t bounds. So even though we don't write down t equals 0 or t equals infinity, that's understood because it's integral with respect to t. 0 to infinity, t equals 0, t equals infinity. These are the t bounds. These are not the u bounds. The u bounds are different. See, the old bounds, the t bounds, are going from 0 to infinity. The new bounds are from, 0 to infinity. Correct. Good. Now, of course, you have to understand, that we didn't just copy. These are actually different. So this corresponds to u equals 0 to u equals infinity. Now, we are almost done. The 1 over c is on the outside. That can be pulled out of the integral. And then we can write this as s over c times u, function of u du. And then we say, how does this compared to that. Because we're thinking in terms of Laplace transforms. And remember, u is just a symbol. I can replace it with any symbol I like. So if you're not comfortable with u, replace it with a variation of t. Does this connect?
The s has been replaced by s divided by c.
Yeah, the s has been replaced by s divided by c. The fact that all the symbols here just switch to a different symbol doesn't mean anything, because it's just a symbol. Symbols can be changed. So what we have is a 1 over c out front. And then this is the same thing as s replaced by s divided by c. So f of s divided by c. That's it. So that's an example of the rule. All right. Well, that one, not so bad. Let's try the next one. Suppose the Laplace transform of f of t is f of s. Now we're going to find the Laplace transform of e to the ct times f of t. Maybe some integration by parts action going on here because we've got two things multiplying together. All right, well that should be good. We got some space here. We can probably fit it in. I hope, maybe. So Laplace transform e to the c times t, f of t. So again, that's just the part I'm plugging in. So I'll put it in the right slot. E to the minus st, e to the c times t, f of t dt. So I'm saying that this is my part I'm plugging in, so I plug it in. Well, can we clean that up? Simplify anything?
The e exponentials can be found.
Oh yeah, it's e to something times e to something, so what happens to those? You can add them. So e to the minus s times t plus c times t, f of t dt. Well, what else can we do with these pieces upstairs? You can pull out the t. You can also pull a minus out in front. E to the minus something times t, f of t dt. What goes here? S minus c. All right. And now stare at this for a moment, not too long. What do we see? It's all like a Laplace transform of what? Yeah. Well, instead of s, it's s minus c. So now we're like, wow, that's pretty slick. Multiplying by e to the ct is basically a translation. Cool. Cool. Good times. Good times. All right. Well, that's not so bad. We should have more of these. All right. You ready for more? Sure. Yes, they say. We're ready. Okay. We'll start. We actually haven't done a function yet. Let's do a function. E to the power c times t. All right. So, well, we start going. So this is definition, 0 to infinity, e to the minus s times t, e to the c times t, dt. But we just talked about this. That's 0 to infinity, e to the minus, in parenthesis, s minus c times t dt. Well, can we integrate this? Because we're integrating with respect to t, so it's essentially e to a constant t. Is that something we can integrate? Yeah, it is. And do you know what it is? What is the integral of this?
The negative s minus c.
Well, you have to account for the constant, so you would divide by the constant in front, e to the minus s minus c t, and then you evaluate. Now here we run into a small technical thing as saying, well, does this make sense? Okay, so we'd like it, so when we plug in infinity, what should be true? Yeah, we'd like it to go to 0. When will that be true? If s minus c is positive. If s minus c is positive, when I plug in infinity, I get an e to a large negative number, which is small. So there's this sort of a caveat down here. We'll put a little parenthetical comment for s bigger than c. Now, most of the time, we don't care about these comments, but there's a small technical thing floating in the background that we never really point to and say, but what about this? Like, yeah, we don't care about that. Okay, Steve, all right, whatever. So let's just assume s is bigger than c. Plug infinity, we get 0. Plug in 0, e to the 0 is 1. So we have really 0 subtract minus 1 over s minus c, which becomes 1 over s minus c. All right. So now we can do exponential functions. Exponential functions, no problem. Okay, well, if exponential functions are no problem, then we can almost right away, with very little work, do some functions which we've mentioned before. Hyperbolic sine, hyperbolic cosine. Now, hyperbolic sine, also known as sinh. Hyperbolic cosine, also known as cosh. And the reason that we can jump into these is they're closely related to exponential functions. They're essentially combinations of exponential functions in some appropriate way. So let's find their Laplace transforms. All right, which one do you want to tackle first? Sinh or cosh? Cosh? All right, so we're going to tackle the cosh. So we're going to go all the way through with the cosh, and then sinh will just say, aha. And then this small thing happens, and here's the answer for that one. So for cosh. So first off, we say, hey, this function cosh is the same as a combination of two exponential functions. So it's 1/2 e to the b times t plus 1/2 e to the minus b times t. Well, what's true about the Laplace transform? It's linear, so we can break it up. So this is 1/2 the Laplace transform of e to the bt plus 1/2 the Laplace transform e to the minus bt. All right, and now what can we do?
It's the same as in the previous.
Yeah, we say, oh, look over here. We know how to do those. So the Laplace transform of e to the bt would be 1 over s minus b. E to the minus bt, 1 over s minus minus b, so s plus b. And we can even make this look nicer. Like I said, we're doing algebra. What's the algebra thing to do here? Combine. So we want common denominator. What would our common denominator be?
S squared minus s squared minus b squared.
Yeah, so it's s minus b times s plus b. So it'd be s squared minus b squared. Then there's a factor of 2 downstairs. Upstairs, we'd multiply the first term by s plus b over s plus b. So we get an s plus b. And then plus. Second term, we multiply by s minus b over s minus b. So we have an s minus b. And if we have s plus b plus s minus b, what do we end up getting? 2s. There's a 2 downstairs. So you get s. S squared minus b squared. And there's the cosh function. All right. Now you might say, ha ha ha, Steve, you fool, you've left no space for the sinh. Well, that's because we're just going to say what changes. So for the sinh, the change is the minus. So there's this plus changes to a minus. 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 So at the end, s plus b subtract s minus b becomes what upstairs? 2b? Or is it not 2b? No, it is 2b. Divided by 2 makes b. So b over s squared minus b squared. And there's the sinh function.
So with these transformations, does that function have the same result as cosh dt?
What do you mean by this function? What we're saying is, if you plug cosh into the Laplace transform, out comes this function. Which, well, now what we're going to do is we're going to have a bunch of these functions combined together with other stuff, which is then going to require us to do some algebra to simplify. And you're probably thinking, Steve, this fun algebra stuff you keep mentioning, what's the magic algebra stuff? It's called partial fractions. Oh, partial fractions, we've missed you. Okay, so that's the fun algebra stuff we get to do with these expressions. And then we go backwards. Going backwards says, oh, if I have something that looks like this, I know it came from a cosh. So if at the end of the process of doing our algebra we say, oh, I have this piece, it must be that my answer has a cosh involved. So that's what we're going to be doing. Okay, so that's sinh and cosh. But you're probably saying, oh, I don't want hyperbolic sine. I don't want hyperbolic cosine. I just want plain old sine and cosine. Okay, we can do those too. All right, using integration by parts twice, we have the following. So this is just given to us. This is good stuff. So this stuff right here, we're just going to take as truths. So this is from Calculus 2. We've learned how to do this. Good times, good times. So, all right, so suppose we just looked up and we said, okay, this is true. Now, it's not so hard to do. It's not trivial. It takes time. But that's not the main point of our discussion today. What we want to do is say, okay, let's use that to find the Laplace transform of sine and cosine. So we'll do one carefully. The other one we'll just quickly point out saying, okay, and here's the main difference. Which one do you want to do carefully? Sine? You saw the sine, huh? All right. So we're going to focus on the sine. All right, so the Laplace transform of sine. So according to the rule, that's the integral, 0 to infinity, e to the minus s times t. Then we plug the function, sine b times t dt. So this part is definition. All right. Next part. Say, all right, that looks like this part up here. The only difference is what we called a is now negative s. So I can write down the right-hand side, except wherever I see a, I write down negative s. So that would be negative s squared plus b squared, e to the minus st sine of bt minus b over s squared plus b squared, e to the minus st cosine of bt. And then we evaluate that from 0 to infinity. All right. Now, this stage. Well, plug in the infinity. E to the minus st, what will happen to that? It's going to go to 0. Implicit in that is the assumption that s is positive. So, all right, so given that s is positive. All right, so those parts go to 0 at infinity, so we have 0. Subtract. Now, when we plug 0 in for t, the sine of 0 does what? 0. So that first term goes away completely. Cosine of 0 is 1. E to the 0 is 1. So we end up with 0 minus b over s squared plus b squared. Well, that's the same as b over s squared plus b squared. And we're done. Now, does this sound familiar? Like we've seen something similar before? Sinh was b over s squared minus b squared. Sine is b over s squared plus b squared. Coincidence? No. We don't believe in coincidences. Or maybe we do, I don't know. But it's not a coincidence. There's a connection. We'll do that in just a moment. Okay, so that was sine. You might say, okay, Steve, what happens with cosine? Well, what will happen with cosine is the following. You have the same kind of setup, and now you just think about the pieces. As t goes to infinity, okay, the exponential term drives it to 0. At 0, the sine term goes away, so what you have left over is the piece at the front. So what you'll really have is you'll have 0 minus, and this piece is the key piece. This is the part that drives it. What's in front of the cosine term. And remember that a became minus s. And so the conclusion is, if you run through the details, you'll get s over s squared plus b squared. All right. So there's sine and cosine. Well, that result is so nice. Let's do it twice. Let's do it again. But now with completely different way. This is the fun way to do it. So we're going to use de Moivre's formula. If I think, my gosh, there's a lot of French names today. Yeah, well, French did a lot of fun stuff. Okay. So de Moivre's formula, what is that? Well, that says e to the power I theta is cosine theta plus I sine theta. And one of the things that you can get from that is sine of bt is 1 over 2i e to the power I bt subtract e to the minus I bt, also related to sinh. And cosine bt is 1/2 e to the I bt plus e to the minus I bt. All right, so we've done sine and cosine already. Let's pick one of these. Which one do you want to try? Sine? All right. You've picked the sine. Interesting choice. All right, so we're gonna figure this out. So the question is, what can we say using de Moivre's formula? So we're going to go a little bit quick here. So according to this is the Laplace transform. 1 over 2i e to the I bt subtract e to the minus I bt. And I'm just replacing what sine is. So the nice thing is that this has become a way to write our Laplace transform for sine in terms of Laplace transform of exponential functions. Now you might say, but does that help us? Well, the constant can come out, and so we have the Laplace transform of e to the I times bt, and similar Laplace transform e to the minus I bt. So what's going to help us here? Well, it turns out that if you come back to the Laplace transform of e to something, we really just needed that this s minus c, you might say, are we okay to have complex numbers up here? And the answer is yes. The complex, everything follows through. Even the part where it drives down to 0. So what we can do is we can use our rules for the Laplace transform of the exponential function e to a constant t. It's going to be 1 over s minus that constant. So the Laplace transform of e to the constant t is 1 over s minus the constant. We're going to use that same rule. It still applies. So that's 1 over 2i, 1 over s minus I times b, minus 1 over 2i, 1 over s minus minus makes plus I times b. And you're probably thinking like, what? Is it really? Okay, well, but remember, we get to do algebra here. So let's do our algebra stuff. So what can we do? Well, we can combine. Combine these together. So in the first piece, I'd multiply by s plus ib and top and bottom. On the second piece, I'd multiply by s minus ib. And I do that on top and bottom. And if I do that, then my denominators line up and everything is happy. So, quick test of your ability to multiply. S minus I times b, s plus I times b becomes, okay, everyone got the s squared part? Good. Then there was a lot of mumbling here. S squared becomes s squared plus b squared. You might say, shouldn't it become minus I squared b squared? Yeah, exactly. I squared becomes a minus. Minus minus makes plus. Okay, cool. So that's our downstairs. So we have 2i s squared plus b squared. Upstairs, well, we have s plus ib subtract s minus ib. What will we end up with? 2 times I times b. The s's cancel, the ib's combine, and now we're in luck. The two i's cancel, so we end up with b over s squared plus b squared. And you might say, is that the same thing that we had before? And the answer is, yeah, it is. It is the exact same thing that we had before. So this is actually a completely justifiable way to also derive sine. Cosine works the same way. If you're willing to cheat a little bit, you can apply the rule we had before about, well, what happens if you scale the inside? It's a slight cheat, but, you know, who hasn't cheated a little bit? Well, hopefully none of you. Hopefully. All right. Next one. So what have we done? We've done exponential, we've done sine, we've done cosine. We want to tackle polynomial, essentially. T to a power. And to do that, we're going to do it by introducing a function. So there's a function called the gamma function. And the reason we call it a gamma function is because we use the Greek letter gamma to denote it. So you might be thinking, that doesn't look like a gamma. That's because it's a capital gamma. Again, learning more Greek letters all the time. Beautiful idea. Now, what is the gamma function? Well, it's defined this way. Gamma of x is the integral 0 to infinity e to the minus t, t to the power x minus 1 dt. And you're probably thinking, that feels a lot like a Laplace transform. You're right. It is a lot like a Laplace transform. So that's why we're going to talk about this function. But it does more. It's not just a Laplace transform. It shows up in lots of interesting settings. Now, some values are easy to compute. For example, if you put in 1, well, you'll have t to the 0, which is 1. Then you integrate e to the minus t. Well, that's an easy integral. And so if you carry out the computation by putting in gamma of 1, you get 1 out. And you're like, okay, that's great. Totally believe it. Then you put in a half. And if you put in a half, you have this weird exponent. You essentially have 1 over the square root of t. And you're like, well, that's kind of weird. And it is weird. It turns out to be square root of pi. And that's a wonderful story, a great story, and not a story we're going to tell. We're just going to go on faith. But it needs a little bit more than what we need, the tools we have right now. For example, if you take Calculus 3, you'll have enough tools that you can show that this is true. But for right now, we're just going to make a little comment saying, hey, you can actually compute this for any value of x above -1. And so, let's see, above -1, maybe it's above 0. So for any value of x above 0, you can compute this value. But we're only going to care about it at the whole numbers. Okay. We're going to do a couple of things. So it says do the following. First thing is, let's connect it back to the Laplace transform. So we want to show that the Laplace transform of t to the power a is related to the gamma function. Okay, so that's not so bad. We start with what the Laplace transform of t to the a is. They even wrote it down for us. That's so cool. Okay. So there's the Laplace transform of t to the a. Now our goal is make this look like that. So now we have to sit here and say, how do we make this look more like that? And what's the hard part of going from here to there?
Getting the S out.
Somehow, yeah, this is the harder part, right? This S here. Now you might say, well, what about the A upstairs? Well, that's not so bad. The A upstairs is not really an issue because that's not really attached to a variable. That's upstairs as where a constant should be. See, this x minus 1 is a constant from the perspective of the integral. This A is a constant from the perspective of the integral. So that's not an issue, but this S is. Okay, so how can we get that S out? What will we do? What are we doing? What are we going to do to get it out? We're going to do math. Okay, all right. Okay, all right. In the interest of time, I'll tell you, we're going to.
ST minus T, something like that?
I was thinking of something called substitution. Yeah, like, oh, yeah, substitution. Sometimes we're like, oh, let's think of the most complicated things when really the simplest things are the best. U equals minus ST. Actually, you know what, we'll just let U equal S times T. I already like the minus, it's just the S I don't like. Okay, so, or if you like, I could say 1 over S times U equals T. Now this might be a little bit familiar. Almost like we talked about this earlier. Because it's essentially the same thing we talked about earlier. Okay. So if we make that substitution, this will become, the bounds will still stay the same because we're going to have, we always work with positive S. 0 to infinity. ST becomes U. T, well, that becomes 1 over S times U to the power A. dt is a 1 over S U. Oh, sorry, 1 over S du. Excuse me. Okay, so that's the dt. Now, our moment of truth. Let's gather things. How many S's do we have downstairs? There's a 1 over S here, there's 1 over S there. Altogether, how many do we have? S to what power downstairs? A plus 1. S to the A from this part, and one more S from there. Now, from the perspective of the integral, those are all constants, so we can pull them out. So that's where the S to the A plus 1 came from. So that's a good sign. Integral 0 to infinity, e to the minus u, u to the a, du. Now, does this look like the gamma function? And if not, what part doesn't feel very gamma function-like? Yeah, the minus 1. Other than the minus 1, we're pretty happy, right? So here's the thing we can do. Check this out. Check this out. It's called plus 1 minus 1. Whoa, I know, I just... This is gamma a plus 1. Everything's the same other than the fact that t has become u. But t becoming u is just saying, hey, I can change my names. It's still the same thing. And therefore, we end up with gamma of a plus 1 over s to the power a plus 1. That checks the first item on our list. All right. So for the next item, I'm going to go a little bit faster. It says, hey, gamma has this interesting property. Gamma of x plus 1 is x times gamma x. Well, that's interesting. So let's see why that's true. So gamma of x plus 1. So according to the definition, that's integral 0 to infinity, e to the minus t. T to the x plus 1 minus 1 would be t to the x. And if I want to relate it back to gamma of x, well, I say, I really want to somehow get that t to the x. I want to subtract 1 from that exponent. So, I know the x being up here is throwing you off. So think about it like t to the 7th. How can I make t to the 7th look like t to the 6th? What do I do to it? Well, divide by t. What else can we do to it? Take a derivative. And that's the key. So what we're going to do is this something really cool called integration by parts. So we're going to do a little bit of u dv action here. Du, the x comes down. Ooh, it's like there's an x there. That's a good sign. T to the power x minus 1 dt. Then v minus e to the minus t. It's very easy to integrate e to the minus t. So we're going to have uv, so minus t to the power x, e to the minus t, and we're going to evaluate that from 0 to infinity. We'll come back and talk about that in a moment. And then minus the integral of v du. Well, notice there's already a minus attached to the v part. Minus the minus makes a plus, e to the minus t. X is a constant. We can pull that out. T to the x minus 1. That's the t to the x minus 1. dt from 0 to infinity. This last piece, do we recognize the integral? It's gamma of x. What happens to the first piece? It'll be 0. Well, why? At infinity, what part of it goes to 0? The e to the negative t. At 0, what part of it goes to 0? T to the x, assuming x is positive, which we do. So you get 0 plus x gamma x, which is x gamma x. All right. So that's the second bullet point. Now the last one says, okay, n is a whole number. Determine the Laplace transform of t to the n. Oop, I should have made these wiggly signs. Well, it doesn't really matter. So we know that the Laplace transform of t to the n, we actually have a formula for that already. It's gamma of n plus 1 over s to the power n plus 1. So the key question here is there a nice way to write gamma of n plus 1? So let's just make some quick notes. What is gamma of 2? Well, 2 is 1 plus 1. So that's 1 times gamma of 1. Gamma of 1 is also known as 1. So it's 1. Aha! Very cool. Gamma of 3. Well, according to the rule, is 2 times gamma of 2. Well, we know what gamma of 2 is. That's just above it. So that's 2 times 1. Gamma of 4 is equal to 3 gamma 3. But gamma 3 is 2 times 1. So gamma of 4 is 3 times 2 times 1. All right, there's a suspicious thing growing here. Gamma of 5, 4, gamma of 4, 4 times 3 times 2 times 1. What do you see here? Factorials. So gamma of n plus 1 is what? It'll be n factorial. And so that's what happens for t to the n. And so that's a nice thing. In fact, one reason that the gamma function exists at all is it says, hey, we really like factorials, but boy, you know, how do you do it like a half factorial? And the answer is square root of pi. Exactly, right? Okay, so that brings us to the end of today. Just on a side note, you may say, what have we done today? This is what we've done today. We found lots of functions and their corresponding Laplace transforms. We're going to keep growing our list over the next couple of sessions. We will have many. All right, have a good day.